survey allow right, over 10 years, all it says to
Okay. Make sure it's working. Okay. No. Okay. Is there a? I thought I had my own pointer, but I'm not sure. Yeah, I don't know if you have one. I may have one myself. Or a stick. It could be a stick. Yeah, stick is fine. Yes, even better. I can swat at the problematic audience. Yeah, I had a colleague once who would. I had a colleague once who used to whip his hands like magnetic fields, like a rotating neutron star, and he would take off people's heads. And that's how it would work.
Oh, does that mean it's 35 now?
Okay, quickly get your refreshments if you're getting into Sorry about the delay.
That's the priority.
Hi everyone, my name is Mariam Hosseini. I'm a graduate student working with Ido Berger, and today it's my pleasure to be introducing Professor Brian Metzger. Brian is a theoretical astronomer. He has 3 undergrad degrees in math, physics, and astronomy from University of Iowa. He got his MA and PhD from UC Berkeley studying the central engines, theoretical models of central engines of GRBs from UC Berkeley. And after that, in 2012, before 2012, he went to Princeton as a NASA Einstein Fellow and did a postdoc there. And ever since 2012, he's been a professor at Columbia. He's also a senior research scientist at Flatiron Institute. He has a bunch of amazing awards, but just to name a couple, he won the Bruno Rossi Award from the AAS, and he won the New Horizon Physics Breakthrough Award. He is probably most well known for coining the term kilonova, which is the light optical and infrared light that's produced when neutron stars collide, but he studies anything and everything transients like TDEs and supernova, all that exciting stuff. Today he's going to be talking about strange occurrences in galactic nuclei. Give it up for Brian.
Thanks. It's a pleasure to be back here to see a lot of familiar faces. Certainly enjoyed my visits here over the years, and it's been a while since with the pandemic. I think this is the first time I've been back in maybe 4 or 5 years. As Miriam said, I usually come and talk about neutron star mergers. We're still waiting on the next LIGO event with electromagnetic emission. I will actually talk about mergers at MIT on Thursday if you're interested, but today I thought I'd talk about something else I've been working on, some strange occurrences in galactic nuclei. I'm going to give you a Halloween double feature in honor of Halloween. We have sort of 2 destructive events involving stars in the vicinity of black holes or their accretion disks. One of them are tidal disruption events. This is when a star is almost completely or completely obliterated due to strong tidal forces near the black hole, feeding it at a very high rate thereafter. And the other is a new phenomenon. You may have heard about it last week from Ricardo Arcodia, gave a talk on this, but this is quasi-periodic eruptions from galactic nuclei. So these are periodic X-ray transients. I'm going to argue that a good model for these may be a star that's periodically crashing into the accretion disk, not quite overflowing its social onto the black hole, but very close. And so this work was done in collaboration with many individuals. I want to highlight the work I've been doing with the Ty Lineal, a postdoc at Columbia, Nick Surin at Ardita, and Odelia Tabul is a graduate student at Hebrew University. Right, so I think we all, presumably many of you know what tidal disruption of a star is. You have a star that's been placed onto a low angular momentum orbit in a galactic nucleus, so it usually comes from parsec scales out, gets placed onto some orbit that brings its pericenter radius inside the so-called tidal radius. This is the radius interior to which the self-gravity of the star is overcome by the strong tidal forces of the black hole. This characteristic tidal radius is given by the star's radius times the mass ratio of the black hole to the star's mass to the 1/3 power, so it's typically tens or hundreds of gravitational radii. So as your star passes closest to the black hole, essentially what happens is it gets torn apart, so the star, half of the star that's furthest from the black hole gets a positive energy and gets unbound and goes to infinity, never to return. The half that's closest remains bound, roughly speaking, it placed on a series of nested elliptical orbits that bring it back to the black hole over a range of timescales. You can estimate roughly by how much the star is bound to the black hole during this process by the tidal potential times the distance across the star. So that gives you the binding energy, and if you estimate what is the orbital period for matter on an orbit of that energy, you get sort of the time scale it takes for the disrupted stellar material to come back to the black hole the first time. And that fallback time is typically about a month for 10 to the 6 solar mass black hole, which are typical of the types of black holes we think give rise to tidal disruption events. So if you have a half of a solar mass, say this is a sun-like star, I'll mostly be focusing on that kind of situation, falling back on a time scale of a month, that corresponds to a highly super Eddington fallback rate at least for, again, this typical 10 to the 6 solar mass black hole. And then this result from Martin Rees and Sterl Finney that the sort of more weakly bound material falls back as a power law in time for something like t to the minus 5/3 for a complete disruption. And so in principle, TDEs are great because they offer probes a unique way to study stellar populations in distant galactic nuclei. If we could use the TDE properties to infer the properties of the stars or the black holes, we can learn something about those populations. And it also gives us a chance to see basically how a supermassive black hole responds to being force-fed matter at a range of accretion rates which start very highly super Eddington and then decline over time. So if you're interested in maybe looking at state transitions in the black hole accretion disk or the physics of how jets are produced, these are in principle great laboratories where we have fairly neat initial conditions defined by understanding this disruption process. One of the big open questions that sort of occupied, I think, the community of theorists for the last decade is this idea of how the debris actually circularizes. This is a series of older simulations by Hayasaki, Stone, and Loeb, but basically just showing that the disrupted debris, in principle, could undergo many orbits around the supermassive black hole. It was thought, and it may still be true, but there's some work that may challenge this, that ultimately, in order to form an accretion disk, these debris streams have to self-intersect and collide and dissipate their bulk energy and thermalize it. And the idea was that they would form an accretion disk which has a characteristic size which is defined by the angular momentum of this debris and should form a disk naively that is at least of order the tidal radius. Okay. And so it was sort of expected that TDEs would be followed by accretion disks that would extend roughly from the tidal radius down to the supermassive black hole. Most of the emission would be, as a good black hole, thin accretion disks, most of the emission would be produced near the ISCO radius of the black hole, where the characteristic thermal temperatures would be of order, tens or hundreds of electron volts. And so it was kind of expected that TDEs would peak in the far UV or soft X-rays naively, and at least the first, candidate TDEs that were discovered in the 90s by Rosat were, in fact, X-ray transients. And so this expectation was borne out. But then in the mid-2000s, when people started discovering TDEs in the optical, some of their properties conformed to this standard picture, but other properties didn't. So this is just a series of optical UV TDE likers that have been assembled. There's now, I don't remember, 40 or 50 of these events. So they rise to peak on a time scale of indeed about a month, indeed about the fallback time of the debris. They reach luminosities of order 10 to the 40, 45 ergs per second. And then after that point, in the optical at least, they decay something like t to the minus 5/3. So everything looks like it's working. The theory is working great. But one thing that didn't really agree were the effective temperatures of the emission. TDEs should not be radiating so much of their energy in the optical. Another way of saying it is if you define a black body temperature for the emission, it's typically only a couple of electron volts, much less than this naive estimate you might guess for the innermost region of this black hole. Another way of saying this is that the photosphere radii of TDEs are about 1 to 2 orders of magnitude larger than this circularization radius or tidal radius, and quite substantially larger than the innermost stable circular orbit of the black hole. So it seems like the TDEs are producing much larger, cooler photospheres than we would have naively guessed, given sort of the compact accretion disk we would expect from their angular momentum budget. Now, there have been several proposed solutions for this. One of them is that the optical emission in TDEs is not actually powered by accretion onto the black hole. Maybe these debris stream collisions are powering emission without even feeding the black hole. I'll come back to that later. Another idea is that there is accretion power going on, but it's being reprocessed by some kind of extended envelope or outflow. And this is sort of the picture that I've sort of come to believe for quite a period of time, that if we do try to feed the black hole at a very highly super Eddington rate with very weakly bound matter, it will form a very structure which is substantially larger than you would naively guess for a thin accretion disk. And so this is some very nice work by Ramesh and Kurd doing general relativistic radiation hydrodynamics of these weakly bound accretion disks, and indeed finding that, at least for viewers that are seeing the event sort of in the equatorial plane of the binary, the photosphere radius can be quite a bit sizably larger than the tidal radius. So this is in units of gravitational radii, and you see this photosphere out here at several hundreds or thousands of gravitational radii. Now, if you observe the event down the polar axis, where the photosphere is deeper in, then you could potentially see X-ray emission. So there's sort of this idea of a unification scheme of TDEs that may depend on your viewing angle. And I think the key point is that, at least if we are feeding the black hole at highly super Eddington rates, we may expect that the photospheric radius could be quite a bit larger than the outer radius we would expect for the angular momentum budget. But I want to emphasize, though, that a lot of these reprocessing pictures, I think it's kind of implicitly assumed that, well, it is assumed that the optical TDE flare is powered ultimately by black hole accretion. And it's also kind of assumed that the light curve is peaking when the black hole accretion rate is peaking. At least that's my interpretation. So we can understand, again, why these things are rising on the fallback time. We need to be feeding the black hole very quickly. But I think there's been some evidence that I think which may be questioning this assumption in recent years, that we are feeding the black hole promptly when the optical emission in TDEs is peaking. There are several, I would say, evidences possibly for delayed feeding of the black hole accretion. One of these is very nice work by Yvette Sendes and Ido's group as well, sort of noticing that in some TDEs, so this is just showing the radio luminosity of TDEs. There are many TDEs where there's sort of no radio detection for the first several hundred days, and then suddenly, several hundreds or even 1,000 days after, you see a very bright brightening in the radio. And this could be possibly an off-axis jet that was launched at the beginning and is now just coming into our line of sight. But it's also, I think, possible that the actual feeding or creation of the relativistic jet is being delayed substantially relative to when we see the optical emission peaking. And there are other examples. This HYZ is just the most sort of striking example of this as a growing sample of these delayed radio jets. We also see in some TDEs that the thermal X-rays, which are nominally coming from the interaccretion disk, their rise is substantially delayed relative to the optical peak. So this is assassin 15OI, where you see the optical was rising and starting to decay, but the X-rays are just kind of slowly, gradually rising to their peak. Now this could be because maybe the opening angle of the jet is changing. We're seeing more of the accretion flow. But it could also be because we're actually delayed in when we're feeding the supermassive black hole. So it's peaking, its accretion rate's peaking out here at 400 days. We're seeing the optical flares at a few hundred days. And though somewhat a little bit more controversial, there have been claims of 3 or 4 very high energy neutrinos following tidal disruption events, spatially coincident on the sky and in time. And these high energy neutrinos are also delayed. They're not happening when the optical emission is peaked. They're delayed by several hundred days. And they're almost certainly coming, if they are real coincidences, this is somewhat controversial, they're almost certainly coming from within the innermost accretion flow, either the jet or the corona of the disk. And so the fact that they're delayed may also be suggesting that the black hole is being fed with some delay. So I would say this is not really strong hints, but I say that there's some hints that maybe the supermassive black hole its accretion rate is peaking a bit after the disruption by several hundred days. So one idea for this, as I mentioned earlier, is that you have delayed circularization, that these debris streams, in order to actually form an accretion disk, it takes them several orbits, and maybe the collision between those streams, the kind of shock energy that's released by that, is the ultimate source of the optical TDE emission. And certainly this has been advanced by Steve Perron and others quite extensively. I will say it's not so obvious that these debris stream collisions can be very efficient at producing. There's a lot of adiabatic losses between the collision point between the streams and powering the radiation. But this is certainly a possibility, but it is challenged by, I would say, some recent models, recent simulations of tidal disruption events. And so this is work by Elad Steinberg and Nick Stone, a paper they published. This is one of the highest resolution studies of the disruption, not the disruption process, but the process when the streams are coming back to pericenter and passing back through the accretion disk. So you create this stream of debris, it goes out, and we'll see it's coming back through the pericenter, and it gets strongly compressed. There's a shock because the strong tidal forces compress the stream vertically. So the matter's coming back through the other way. And what they find is that there's substantially more heating of this debris at the pericenter nozzle than was previously found. And so rather than remaining a thin stream, it basically thickens considerably and starts to collide with the inflowing material. And by the end of their simulation, which runs for about 60 days, for about one fallback time of the majority of the matter, they don't have a stream anymore outgoing. They just have this large quasi-spherical envelope which is surrounding the supermassive black hole. And the reason, I still think they're sort of dissecting exactly why their results disagree with previous analytic estimates for the dissipation, but it has to do with the fact that these streams, as they go into apocenter, they get heated by hydrogen recombination, and so when they come back, they're thicker, and if they're thicker, they get slammed together more strongly from the vertical tidal forces. And so, anyways, by the end of their simulation, they find that basically the entire star, this is just for a canonical 10 to the 6 solar mass black hole disrupting a solar mass star. And they don't find the formation of accretion disk, they rather find this sort of creation of this large quasi-spherical envelope, which has a very shallow density profile, something like 1 over R. And so in fact, most of the mass is not down near the black hole, it's in a very large virialized structure. Most of the mass is out on 10 to the 14 or 10 to the 15 centimeter scales around the black hole. And so this kind of motivated me. It looks actually sort of quasi-hydrostatic in its structure. It looks like it's supported by the thermal pressure that's been dissipated by this collision. So this motivated me just to think about the general problem. What if I did form, actually, rather than a disk, a hydrostatic structure around the supermassive black hole? And I'm not the first person to think about this. Actually, Avi, a long time ago, was thinking about this as a model for TDEs. But let me just go through the arguments. If you did form a spherical envelope around the black hole with a binding energy equal to about how much the half of the disrupted star is bound to the black hole, if you were to create a virialized envelope with that binding energy, what would be its size? Well, it's a few lines of algebra to show you that it would create a virialized structure which has a scale which is of order the star's radius times the black hole to the star's mass to the 2/3 power. So you can actually naturally create a very large structure, 10 to the 14 or 10 to the 15 centimeters, just by thermalizing this material. This is typically a factor of 100 times larger than the circularization radius. And so this sort of characteristic size of this envelope, if you were to form one, is actually very similar to the photosphere radii that are observed in TDE flares, optical TDE flares. So this is a compilation of ZTF events by Yao, and I'm just plotting the black body radius as a function of the black hole mass. This is a proxy for the black hole mass because we're really measuring velocity dispersions in low mass galaxies, so it's quite uncertain. But nevertheless, just even, and I haven't accounted for possibility of different stars being disrupted, but just driving a line through these photospheres, I'm not saying it's the perfect fit by no means, but just the order of magnitude of these physical scales is, I think, produced by what you would get if you did form a quasi-spherical envelope. And because it's substantially larger than the circularization radius, that's another way of saying this envelope is rotating very slowly relative to Keplerian. So it's not supported by rotation on this scale, it's supported mainly by radial pressure or possibly convection. So this is not a new idea. This goes back to Loeb and Ulmer. It's also kind of in a different context been pointed out by Coughlin and Begelman. Now, of course, you do need a black hole disk on small scales. So this sort of motivated me to think about a very highly simplified model for tidal disruption events, which I'll call the cooling envelope model, where I think that the point is I'm thinking of the driver not necessarily as the black hole, but the evolution of this outer envelope. So you're sort of thinking about sort of two structures. You have an envelope and you have an inner accretion disk. I'm basically solving for the evolution of the mass and energy of the envelope. So the envelope gains mass by the fallback streams, which we expect mostly will be dissolved near apocenter. It can also feed onto the black hole. And we follow the energy of this envelope by accounting for the rate of losses from its surface. It's radiation pressure supported, so it has to radiate at its Eddington luminosity if it's higher static equilibrium. Well, we do allow there to be feedback from the supermassive black hole accretion in the center. And then basically the accretion rate into the black hole is set by the density of the disk at the circularization point, which I imagine is where this envelope attaches onto something like a disk. And then you parameterize the accretion with some kind of alpha viscosity. And so, given the parameters of the model, the mass of the black hole, the mass of the star, initially how bound it is by the disruption process, you can predict, how this envelope will evolve in time, the radius, its luminosity, effective temperature, and then also it gives you some estimate of what the black hole is accreting. So what I want to just say is that, what we're finding when you run these models, and I'll show you some explicit examples of the light curves. This is not purporting to explain the formation of the envelope. I'll leave that to Steinberg and Stone to tell me how this envelope forms. I'm just saying after that point it forms, let's follow its evolution. And what I will say is what I find is that the envelope cools from the outside by radiation for the density profiles that are motivated by those simulations, or most of the mass on large scale. It cools from the outside faster than it accretes onto the black hole. So at least at early phases, the rate limiting step to feeding the black hole is not necessarily the time it takes to form, circularize, or accrete. It's actually a cooling time that it takes this envelope to contract to high densities where it can increase the accretion rate onto the black hole. So this actually, the simplest case, if you ignore the feedback from the black hole, which does happen, it resorts to 19th century physics, which is Kelvin-Helmholtz cooling. So I'm just going to go through this if you don't remember your Astro 101. So we have a black hole envelope which is being forced to radiate near Eddington luminosity. There will be a Kelvin-Helmholtz time, which is the time it takes to basically reduce its binding energy or increase its binding energy by a factor of 2. So that's just the binding energy I gave you earlier imparted by the disruption process divided by the Eddington luminosity. So that gives you a Kelvin-Helmholtz time, which is typically also around a month for the initial size of the envelope. And then if you just let it contract, the radius will drop as power law 1 over time. Because the luminosity is basically fixed by Eddington, the effective temperature rises as power law t to the 1/2. And if you're in the optical band, in the Rayleigh-Jeans part of the tail, because these effective temperatures are in the UV usually, then your luminosity will decay as t to the -3/2. which you'll see in a second is coincidentally similar to t to the minus 5/3. So this results in, so if you ignore any addition of mass to the envelope, which is simplification, but this results in a number of predictions, okay, that TDEs should be more luminous if they're occurring around more massive black holes. Their photospheres should contract after the TDE. They should get hotter, the photosphere should get hotter, and the optical band light curve should decay something like, t to the minus 3/2, which is coincidentally similar to t to the minus 3/2. So I'll just go through these. I'm not going to say any of these are not perfect matches to the data, but they don't look terrible. So if I just take this again, this Yao et al. Sample of black body luminosities of TDEs versus the black hole mass, again, there's lots of dispersion. We don't really trust this axis very much, but it does, if I squint my eyes, it does look like there's possibly some correlation there. That seems like the more massive black holes are brighter. What about the photosphere contracting or getting hotter in time? Well, again, I don't purport to explain the formation of the envelope, what's happening near the peak. But if you squint your eyes at the photosphere radii of TDE flares, they do seem to be contracting and getting hotter. And this is not accounting for any outflows or anything from the disk. But yeah, individual events, so it's messy. This is, if you calculate what would be the convective velocities needed to carry out this luminosity, they're nearly sonic. So this is very messy structure. But at least you could see a trend if you glaze over your eyes and look at the average. You could see things are getting hotter. They are contracting. Maybe there is something to this model. So what we did was this is just an example of this cooling envelope model. It predicts, again, after you form the envelope, how the luminosities, effective temperatures, and then a proxy for the black hole accretion rate. Because in this model, the accretion rate is initially low because the density near the black hole is low, but as it contracts, the accretion rate rises. So you have these 5 parameters: the black hole mass, star's mass, how deeply penetrating this disruption is. There's a feedback parameter, what fraction of m dot c squared goes back into the envelope, and then the viscosity of the disk, which controls the feeding. So what we did, just to make this more real, is actually apply it to some data. This is with Nick Sarin. We basically did parameter inference on the model applied to a set of 15 tidal disruption events, mostly, again, from ZTF. I wouldn't say we sort of parameterized the rise phenomenologically, and then basically the model predicts the decay, and then we're trying to infer these different parameters for individual tidal disruption events. And so this is the kind of thing we get for the black hole masses, the stellar mass. I'll come to these other ones in a second. The penetration factor is not well constrained by the light curve data. And then on the bottom here are sort of running histograms of the black hole masses and stars' mass. And I don't claim anything too profound here. These are sort of the predictions you get from lost cone theory. You naively expect there to be a higher disruption rate for lower mass black holes. You do expect there to be more lower mass stars, depending on your IMF. You have to slightly modify the IMF for the disruption rate IMF. But anyways, it's not crazy, at least. Needs to be improved. So the final thing these models predict is the time it takes for the disk to sort of fully contract, if you will, to form the accretion disk. And so the physics here is really one of a cooling delayed supermassive black hole feeding. So the basic idea is that you're going from something that's more envelope-like to something that's more disk-like. As I mentioned earlier, if you neglect the feedback, the radius is declining as 1 over r, so you can kind of estimate when it will contract to the circularization radius. And that's sort of the minimum time scale. That roughly defines a time scale in this model wherein the accretion rate reaches its maximum. And if you go through the numbers, this works out to be roughly a year or so. Now, if you go to very late times in TDEs, it does look like, years or decades after, it does look like there's a thin accretion disk there, an unobscured accretion disk. But this is saying that there's some transition phase from this sort of more spherical envelope. And so to me, this is a possible explanation for some of this delayed activity, these late rising radio flares or delayed rising X-rays. Maybe it's because we actually have to wait for the density near the black hole to rise from external cooling. I will say there's an entirely different model I've worked on for why jets may be delayed in TDEs. If you don't like the first scenario, listen to the second one. This was done with Odelia Tabul. It basically points out this fact that in general in TDEs, the orientation of the accretion disk will be misaligned with the spin axis of the supermassive black hole. And so if we think that the jet is coming out along the accretion disk axis, that jet will precess with these thick accretion disks precess, we think, as solid bodies, and so there'll be a precession of the jet around the spin axis. And there will be this whole dense medium surrounding the black hole because of the accretion disk winds, and so we argue that it will be more difficult for one of these precessing jets to get out of this envelope. But then over time, the jet will align with the spin. There are various processes, either magnetic or hydrodynamic, which can cause alignment. And once it does, it's easier for the jet to get out. And so that delayed in terms of the alignment may also cause a delay in terms of when the jet gets out. And more powerful jets tend to align faster because they can align through an MHD mechanism. And so that could explain possibly why we see some very powerful promptly escaping jets in some TDEs where they have a lot of magnetic field on the black hole, and other events where it takes a while for the jet to align and get out. So I encourage you to read this paper for more details. Okay. So that's sort of the first half of this double Halloween feature. I'll just summarize it by saying, I don't think it's clear to me that rapid circularization, meaning spherification, necessarily means the black hole is going to get fed rapidly. I think the debris wants to form a kind of quasi-spherical object, and I think it's possible. I think Rush and I need to discuss this more, but I think it's possible that the tail wagging the dog is cooling from the outside initially before the black hole starts controlling the game at later times. And if you do assume that it takes a few months to a year to actually cool, then the black hole accretion rate could be delayed, and this might help explain some of these delayed black hole signatures. But we really need to do longer-term GRMHD simulations that can follow the cooling phase of these events. Okay, let's see, how am I doing for time? Anyways, I'm going to just segue into my next topic, which is very different. This is related to, but it also is related to bad things happening to stars in the vicinity of black holes. This work was done with Itai Lineal as a postdoc at Columbia. You can read about our paper here. So this is a model for quasi-periodic eruptions, which I'll tell you what they are in a second. You can get the basic idea already. So quasi-periodic eruptions, you probably heard a talk from this by Ricardo last week. There are only 4 of these systems known. They've only discovered, I think, in 2019. They are periodic outbursts from galactic nuclei. The periods are typically a few hours to tens of hours. The flares themselves last for roughly an hour, give or take, so the duty cycle of the flares is around tens of percent. The flares reach peak luminosities of order 10 to the 42 ergs per second or so, and they have temperatures in the range of a few hundred electron volts. This may sound soft, but it's not as soft as the actual quiescent black hole accretion disk, so we can observe these flares on top of what is potentially an existing accretion disk in the system. The black holes, the galaxies that host these are quite low in mass, so the supermassive black holes are probably low in mass. This is just an example of something like 15 straight QPE flares detected from one of these sources by, this is nicer, I think, that detected this. So you see they're very, very distinct and high amplitude. They stick out from the quiescent emission by order of magnitude or more. The leg curves of these quasi-periodic eruptions look like this in different energy bands. They tend to be narrower and peak. They tend to be narrower and peak earlier in the harder X-ray bands, and then they're broader and softer in the weaker X-ray bands. They appear to be quasi-thermal spectra for the flare emission, but when the flares are going away, in between the flares, you also revert to seeing a quiescent emission, which is probably coming from a black hole accretion disk. There's a lot more. You can talk to Ricardo more about this. There's a lot of complicated phenomenology with the shape of these light curves. But the most interesting thing is probably that they exhibit this quasi-periodicity. Okay, so there are, roughly speaking, out of these 4, there's 4, I would say, confirmed QPE sources, and there's a couple that are potential sources. They're sort of among the 4. There are kind of 2 classes. They each have 2 sources. We'll refer to them as the regular and irregular ones. The regular ones is what I'll mostly focus on because you might be able to make sense of them. The irregular ones, it seems like they're sort of chaotic in when the flares are arriving, at least to me. The regular ones are very fascinating because the flares are not strictly periodic, they're quasi-periodic, so they don't arrive in exact intervals, but the duration between two consecutive flares oscillates. So it starts off very short, and then it gets longer and shorter and longer. So this oscillation in the T1 versus T2, typically around tens of percent or so. So it might oscillate, as you say here, between 8.6 hours and 9 hours, 8.69, okay, like this. Okay, so one of the interesting aspects of these, and this is, you see this in different, you could come back to the same source, several months apart, and you would see the same behavior. So one of the interesting aspects of these QPEs is that there seems to be some association with TDEs in at least a couple of QPE systems. When you look back, you see that the quiescent emission from the same nucleus was brighter in the past. Okay, so this is the best studied source is GSN 069, where the QPEs were actually discovered in an observation, I think in 2018 or 2019. But there was an outburst from the same nucleus in 2010, and over the ensuing decade, the X-ray emission has been declining in time. And then there's also that additional QPE association from Johin Chakraborty and Aaron here. So it seems like out of this small sample of events, there's some reason that TDEs like to happen in these galaxies before we see QPEs coming from them, which is quite intriguing. So there have been a number of theoretical models for these, more models than QPEs at the present. And I'm not going to go into all of them. A lot of them involve, in fact, even the first model I worked on for these sources involved some kind of star orbiting the supermassive black hole. And every time it goes through pericenter, it was overflowing its Roche-lobe and dumping a bit of gas onto the black hole, producing a flare, and then it would go back out. I think it's very challenging for these scenarios to explain at least this subset that have this alternating behavior. Because why would the time between two flares vary? If it's on a periodic orbit, why would it change by 10%? When it's going through pericenter, should be strictly periodic. Okay, in other words, this would be an orbital period, but we're actually seeing this oscillating behavior. So this phenomenologically motivated observers before us, but us in particular, to focus on this scenario where QPEs are produced by a star which is orbiting the supermassive black hole and colliding with its accretion disk, and basically twice per orbit it collides, and you see a flare twice per orbit. Okay, I'll explain in a second how this could explain some of these observations. I'll go to this into some detail, but the idea is that when it hits the disk, it creates this hot cloud of debris which generates the flares. And so you would expect, for example, this can explain this irregular timing, because if you postulate that the body is on a mildly eccentric orbit, it will spend a little bit longer on the apocenter side of the orbit than the pericenter side. So the duration between the flare there and there will be slightly longer than there and there. And so this can explain this oscillation in terms of when the flares are arriving. And so in this scenario, the actual orbital period is twice the mean of these two periods. So you'd have orbital periods of 5 to 18 hours, which would correspond to being outside of the Roche radius of the black hole for typical side of solar mass stars. And actually, it's quite expected if you bring in stars into the galactic nucleus, extreme mass ratio inspirals, things that are not tidally disrupted but on quasi-circular orbits, it's actually expected that a large fraction of them will have moderate eccentricities. So in order to explain 10% variations in the arrival times, you need eccentricities of order, tens of percent, could be higher, but that kind of makes sense. So how are the flares themselves produced in this scenario? Well, the idea is that the star is passing through the disk which is presumably reasonably thin. The star is passing through the disk at a highly supersonic speed of order the orbital speed, which is, in this case, for these orbital periods of order 1/10 the speed of light. So it will collide with gas in the disk, which is roughly defined by, if we're talking about a physical stars with a physical surface, the effective cross-section for interacting with the disk is roughly the geometric cross-section of the star, because gravitational focusing is not really relevant because these are much higher speeds than the escape speed, and the disk sound speed is presumably lower than this. So you get a supersonic collision, and so the amount of mass you carve out in the disk depends on its structure If you model it as an alpha disk, it's around 10 to the minus 6 solar masses for a typical value of alpha and a typical accretion rate in Eddington units, which you could fit to the quiescent emission. So that's a typical number to keep in mind. You're punching out around 10 to the minus 6 solar masses per orbit. And there have been simulations of these star disk collisions, but actually they go back into the 90s. And I'll guarantee you in the next few months there'll be many more simulations of these appearing because of this problem. But this is a simulation from Ivanov in 1998 where they're actually sending a black hole through an accretion disk, but it's kind of the same thing. You replace the star's radius with the Bondi radius. And so what you find is actually, so you might be asking at this point, how did I see a flare from both sides of the disk if the disk is optically thick and I'm shooting through one side? Shouldn't I only see a flare on the side the star is going through? Not the case, because you shock heat the matter and then it's high pressure and it expands both above and below the disk. And so the analogy we use for this is the bullet going through an apple. You don't just see the shreds of the apple coming out the direction of the bullet, that also comes out the backside. So your star that's going through the disk, if you did see emission from the debris cloud, would you be able to see it from both sides of the disk? And so how would you estimate the properties of this flare? Well, it's very much akin to creating a little miniature supernova on top of the accretion disk. So you're imparting the debris with a lot of thermal energy, which re-expands, so it accelerates back to a order the orbital speed. So you have this expanding debris cloud, which is moving almost as fast as the star. Initially, the optical depth through the disk is very high, so initially the radiation is trapped, but once that sphere expands a few orders of magnitude in size, actually a factor of 10 in size typically, you reach the condition where the radiation diffusion time is shorter than the expansion time, so the radiation can actually get out. And the time scale for that is the same as in the supernova problem, given the ejecta mass you carve out of the disk. And so this works out to be a fraction of an hour. Now, the luminosity or the radiated energy is basically the initial thermal energy you deposit by the colliding star, but you have to account for the losses due to the adiabatic expansion, the fact that you shock heat the matter here, but the radiation is trapped, so it has to expand adiabatically before the radiation could start to get out. And so given the amount of radiated energy and the time scale, you can predict the peak luminosity, and you get something that is, you could scale, it turns out, in terms of the Eddington luminosity of the black hole. So it's roughly given by the Eddington luminosity of the big black hole times the ratio of the star's radius to the orbital radius. So given we're typically, what we find is that we typically require kind of solar mass stars. So this might be of order 10 to the 11 centimeters, and this might be, these are orbital radii of around AU, so these might be 10 to the 13 centimeters. So we're typically a few orders of magnitude below the Eddington luminosity of the black hole. But that's okay, because these are hard flares. You can see them above the quiescent emission. Now, the one thing you get wrong with this sort of very simple analysis is the peak temperature of the emission. If you assumed that the gas and radiation were in equilibrium and you calculate what should be the black body temperature given this emission size and radius, you get a value which is too low. It's typically in the ultraviolet. But what we realize very quickly is that the ejecta won't have time to reach thermal equilibrium with the radiation, and the gas won't have time to come into equilibrium. So black bodies are what you get when you have enough time to create the photons to make a black body. But in this case, like the supernova shock breakout problem, we only have a finite amount of time before that shock-heated gas expands out of the midplane. And you can only create photons in this case as fast as you can create them through black body radiation and Compton upscattering of free emission. And so what you figure out, anyways, what you figure out is that the emission should be harder than the naive black body estimate by some ratio, which you could calculate based on the midplane disk properties, and it tends to be larger than 1. So if you share the same energy density with fewer photons, it's obviously going to be harder. So this is a way to kick your flare temperatures from the naive value you would guess UV up to hundreds of EV. So the idea here is that the disk itself is fairly soft, but the flare, I draw it as a black body here. We actually think it will be a Comptonized free spectrum, but work is ongoing to calculate that spectrum. But with this naive model with Itai, we just said, okay, let's see if we can explain the flare luminosity, the flare temperature, the flare duration, for different reasonable values of the star's radius and accretion rate onto the supermassive black hole. We only have two events, two objects that exhibit this long-short behavior. for the flare properties. But we kind of see the right trends that for longer QPE periods, we expressed everything in terms of the observable orbital period. And we kind of see the right trends that we can explain the characteristic durations for different masses of the supermassive black hole, the flare luminosities. And the temperature is very sensitive to the density in the midplane. So if we can understand what's setting that, these are potentially powerful probes of the properties of these accretion disks. Denser disks got a pretty softer emission. So what about the spectral evolution of these events I mentioned at the beginning? The fact that they're hard and narrower at higher X-ray frequencies, they're narrow and at high X-ray energies, and then they get broader at low X-ray energies. I want to make an analogy, since I mentioned earlier, these are like little miniature supernova on top of the accretion disk. I want to make an analogy with actual supernova, type 1a supernova here, where you see that the redder bands are, in fact, produce wider light curves than the bluer bands. And this is, again, it's just because, initially, when the ejecta is hot, it's expanding. Those layers are expanding quickly. And then at later times, as the photosphere recedes, you get slower layers, which expand slower. And so that's why things evolve slower when they're redder. And I think it's something like that is happening in these events. Same qualitative, at least, behavior. But there's more complicated than this. Talk to Ricardo. So what is the association? I'm running out of time, sorry. What is association with TDEs? Well, okay. So the idea is that an EMRI star comes in, a star comes into the supermassive black hole on a quasi-circular orbit through gravitational waves. This, in general, can take 10 to the 6 years to reverse the range of radii where it would be interacting with a TDE disk. So there's always this flux of these extreme mass ratio inspirals coming in just like TDEs, but they're not being immediately disrupted by the black hole. Then we have a TDE. So it takes 10 to the 6 years for the EMRI to overflow its Roche lobe. And the rate of TDEs in every galaxy is 1 in every 10 to the 4 years. It's almost necessarily the case that every EMRI that's coming into the nucleus like this will experience at least one TDE in its lifetime. Okay? And so after the TDE fades and after the disk gets thin enough and cool enough, if there's this orbiting EMRI in it, it will be able to eventually sort of pop out of the TDE. So what are the relative rates? Well, we think TDEs happen once every 10 to the 4 years in a galaxy. These EMRIs can happen once every 10 to the 5 years if they're formed through the Hills mechanism, depending on the binary fraction. So the number of TDEs, the fraction of TDEs that should have a QPE orbiting in them, is roughly given by the ratio of the EMRI rate to the TDE rate times the number of TDEs that one of these could survive. So if it survives one, even if it survives one, if these are the right rates, we could expect 10% of TDEs to have these popping out of their light curves. So it does actually expect that these should be fairly common. And the final thing I'll say is we expect these stars to actually survive interaction with the TDE disk. So when the star passes through the midplane, it has matter stripped from it, much like when a supernova blows up next to a star. And you can estimate how much mass is stripped. It's not that much, 10 to the minus 6 of the star's mass. But it experiences many, many orbits at once every few hours. So over the course of decades, that should eventually whittle down the star and destroy it. And in fact, with GSN 069, I mentioned earlier, where the X-rays from the TDE were fading and then they started observing QPEs, there was a second outburst from the same nucleus. And the observers said, okay, this is a second TDE, or maybe it's a partial TDE after the first TDE. So I thought at this time, okay, this is just the star being destroyed. So if we had the first TDE, and then the star, loses mass and inflates, and at some point it gets destroyed, either overflowing its Roche lobe or being destroyed. So I thought this was the second TDE. Observers, Ricardo and others, kept observing this system as it faded from its second TDE, and the QPEs reappeared. So to finish my Halloween theme, it's alive. It doesn't seem like the QPEs have gone away. They reappeared. Whether that means this was actually a second TDE, whether this means the accretion disk is acting non-linearly with the star to make an outburst-like behavior, I don't know. But what is interesting is that the timing has changed now. So the timing between, so the first observation they did, they only got 2 bursts. So they didn't actually see the whole burst sequence, the long, short burst sequence. But now it appears that the first 2 have gotten longer, I guess it is. The interval, Ricardo can correct me. It got longer between the first 2. Now, if this scenario is correct, if there really is an orbiting body, it would be very difficult to change the orbital period. We could change its orientation. So if it's on an elliptical orbit, we could change the time between the 2 bursts. But the total sum should remain the same. So we're waiting with bated breath as the observers monitor the system again. If they observe that the pattern was retained long, short, but now with just different amplitudes between these, then it seems very likely that this is actually a star. And this is the final slide, which is just to say on the timescales we monitor these systems, we do expect that the star's orbit should exhibit substantial precession, both apsidal and nodal precession around the spin of the black hole on human timescales. And so several authors have proposed that by monitoring this, we could do, for example, constrain the supermassive black hole spin. So I'm basically finished. My conclusions on this section are stellar EMRIs, I think, should be common around supermassive black holes on this scale where TDEs are happening. So if an independent TDE produces a disk, we're going to get interaction of those stars with the TDE disk. This could explain QPE flares. And then how many would depend on whether the EMRI can survive. So I think this is very exciting because these could offer new probes of processes in galactic nuclei. Not stellar EMRIs, but black hole EMRIs are LISA sources. And actually, if there was one in the galactic nucleus, I think LISA could detect even a star orbiting the supermassive black hole. I didn't discuss other things that this style model could also be applied to big black holes, supermassive black holes colliding with their disks, and the possibility that we could actually have this QPE phenomena also in the UV range. But with that, I will finish and take your questions. Thanks.
Yes, now we'll take questions. Thank you so much, Brian, for that great talk.
So, what do you think? Is it on? No, it's not. It's not on. Okay. So, could you comment on the connection, on the potential connection between TDEs and changing state AGN or changing look AGN? So, have we seen at least a single case when after the TDE has occurred, we would see like a source of an active nucleus after the TDE is?
That's a good question. I'm not sure I'm the best person to answer. So you're saying whether we see after a TDE that
it started the activity period.
Whether we see it triggered an AGN or something like that. I'm not aware. Maybe Ido, or do you know? I'm not aware of a triggering. I mean, certainly there have been claims of possible TDEs in AGN nuclei, and so that's an interesting question because the debris streams not only interact with themselves then, but also pre-existing AGN disk. But I think there is probably a continuum of how we really disentangle TDEs from long-term AGN activity. But I'm probably not the best person to think about this. Maybe is Morgan around? Yeah. Sorry.
You answered my question, which was going to be about the precession timescales. But I'm curious, how big is the orbit of the star compared to the TDE disk?
Yeah, so it can't be much. So we're finding that the orbital radii, if this really is a solar mass star, then that, as I mentioned, the tidal radius might be tens or 100 gravitational radii. And so these orbits are just a little bit outside of that. So they might be 2 or 3 or 4 tidal radii or something for our orbital periods, so, right? Because it's sort of related to the mean density of of the star, the tidal. So they're not much long. They're very close to overflow. These QPEs have to be very close. But if they were on much longer orbits, they wouldn't be able to interact with TDE disks because the TDE disks only form once they do cool and form. They're only going to have scales of a few tidal radius. So outside, there could be many TDEs that happen, and there's a star that's on a large orbit which just doesn't interact.
Yeah. So can there be these kinds of objects where you're not seeing the sort of split period because you're not seeing the thing collide with the disk at apocenter?
Right. You mean I see. So you have systems where you only get one collision per orbit. Yes, and that could be. That could explain some of these irregular ones. I'm not sure. I have to think about how much you could change the timing of the orbit. But you're right. If it only interacted once with the disk, you would just see one. You wouldn't. Yeah, it would still be periodic, right? But
and then you would, if the thing precesses,
Yeah.
You can go from one state to the next if it is so what you're seeing is moderate eccentricities,
Right.
but you may be seeing maybe evidence of higher eccentricity ones that you don't.
Right. Yeah. Yeah. Exactly. So as I said, four of these out of these four QPE sources, there's the two that have the sort of fairly well aligned behavior like this, and then the other ones have this sort of more random. So if there was enough effective precession to really change the collision time. I think the other thing is that the disk itself could be undergoing its own precession, right? So that could also change the timing.
Thanks. So you already mentioned OJ287, but are there any qualitative differences between having a star and a black hole punching through the disk?
That's a good question for people to simulate. Our intuition is that it should be similar if you equate the star's radius to the Bondi radius. Okay. So the reason I think this is a star is that in order to explain the luminosities, I need an effective size, whether that's a physical radius or a Bondi radius, which is of order a few solar radii. So I can do it either at these collision speeds, I can do it either with a physical star, which is a common type of thing that exists, or I could do it with an IMBH. So if I crank up to 1,000 solar masses, I think the issue I have with invoking all of these as being IMBHs is that you would be feeding the supermassive black hole a lot of IMBHs to explain the rates. So I'm a little worried if you wanted to explain. I mean, these are not that these are occurring in once in every. Ricardo can correct me, but like once in every 4 galactic nuclei, every 10 to the 4, not 4. One in every 10 to the 4, 10 to the 5 nuclei has one of these. So my only concern with IMBH is just that if we observe these in a large fraction of nuclei, and we know how long it takes an IMBH to feed the black hole, we might be growing the black holes too much by IMBHs.
Brian, very stimulating talk. So the first part,
Yeah.
this cooling envelope,
Yeah.
it's a great idea, it makes sense. But along the way, you said something about density goes like 1 over r.
Right.
Is that a natural slope? Is it necessary in your model?
If I make, yeah, so I think that was what Elad found roughly as the initial condition. Now I agree that when you start driving convection and energy transport, you're going to change the slope. It will evolve. So I think the question is how does that evolve? So in Avi's original model, he took 1 over r cubed, which basically results in an envelope which is too tightly bound given how initially it starts. So I think it has to evolve from the initial condition into something, if you said it was a convective envelope and it tried to find a constant entropy slope, I think that corresponds to 1 over r cubed. So that would start to so I think there's I guess the question is how. I'm not doing that self-consistently. So the question, that's what I want to understand, is how does that density slope evolve? Because if it starts concentrating the mass at smaller scales, then the black hole feeding will become important faster. So I don't know the answer yet, but it's a great question.
We have an online question from Chief Hung. There's 2 parts. I'll give you the first one. If the QPE comes from a star crossing the disk, why does it turn off after a few orbits?
It doesn't. The QPE doesn't turn off. Maybe I'm misunderstanding this final observation. I mean, these are very costly. I'm not the observer, but these are very costly orbits. So the fact that they only saw the 2 here was just because their observation stopped. It's not that there wasn't an extra one here. So I don't think that it does. In these cases where they've observed, it does disappear during this outburst, but that appears to be just that the quiescent disk is outshining it. So it could still be present potentially, even during this phase. And I don't know before it's so there's sort of this notion that when the quiescent black hole is bright enough, you don't see them, and then when the quiescent black hole gets dim enough, you see them, and then it gets brighter, they go away. But they may still be there the whole time.
I'll accept that on his behalf. Second part, why was there no gamma ray detection for any TDEs, including jetted ones?
Well, that depends on what you think. Let's remesh that. That depends on what you think is the particle acceleration process in the jet, right? If there's some internal reconnection or shocks, they're accelerating particles, and for some reason they don't get high enough energy. So this is a good question, but I'll ask Ramesh. Can you?
No. The first injected guy, which Edo, among others, discovered, was detected by FATS.
Yeah, it was detected by
Yeah,
bad to be a GRB.
What?
Swift
Yeah, it was. I think it may depend on one's definition of gamma rays. Yes.
But not TDEs, but yeah.
Right. So it does. Yes, it was. It triggered. Yeah, it triggered Swift multiple times. It was. I don't think it was detected by Fermi though. Fermi.
No, it wasn't.
Yeah, which is just a product of it being fairly soft.
Is the luminosity of the QPEs related to the mass accretion rate onto the hole? Because in case it should evolve with the decay of the tidal disruption events. I think it was in one of your slides, something like depending
yeah,
on
we
that.
actually find when you scale everything out, we find that yeah, it was in one of my slides, but when you scale everything out, it actually doesn't end up depending on the accretion rate very sensitively, because if your accretion rate's higher, you hit more mass, but it has a higher optical depth, so it has to expand more before it can radiate, so the efficiency drops. So the accretion rate doesn't. The accretion rate does affect how bright the quiescent emission is and whether you're able to see these flares on top of the accretion disk spectrum. But no, I don't think it affects very sensitively the flare itself.
Then the related question was, how do you explain that one was up and one was down?
Oh, okay, yeah. So that's because even though I gave you the, even though I gave you this analogy, there's not. This side is not perfectly symmetric. So well, there's also differences. I mean, maybe the disk is not perfectly smooth, but yeah, the idea is that when one is that you're seeing one side versus the other side in consecutive flares. So if there's any asymmetry here, which there is, you would expect there to be some differences. I mean, they're not enormous differences if you look at the data.
Yeah, my question was,
like
at the beginning they're really similar. When it reappears, they instead are really different.
I think the notion is when it's reappearing, the binary or the disk has evolved into a new configuration. So it may be that it may be that this is no longer consistent with a low eccentricity. Maybe we need a 0.3 eccentricity, but we've changed. So our model is just the simplest thing. I'm coming in head on, but in reality, it's coming into an angle. So there's different things that could affect the relative brightness here. But we haven't modeled that.
Hi, thanks for the lovely talk. My question is actually on the TD part.
Okay, great.
So you've compared a lot with the optical properties or the optical TDs.
Yeah.
Do you have a sense as to what's happening regarding the dichotomy with X-ray TDs? For instance, the X-ray TDs from Rosita from the Russian side, or the one that will come out soon from the German side. Most of the X-ray TD candidates can't even be confirmed because the optical is doing nothing. No lines in the spectra, no optical TD. So if you only see X-rays through the funnel, wouldn't you expect like a much smaller rate of X-ray TDs?
Yeah,
but they're actually comparable.
I think my statement that a disk is delayed in forming is predicated on me normalizing this to 10 to the 6 solar mass black hole. So I think there's two ways you could get faster formation of a disk. One is if you have a higher mass black hole, everything's lower density, this thing just cools a lot faster. Also, the accretion rates are not as super Eddington. So my guess is that higher mass black holes will produce things that look more like the canonical picture of forming a disk. And so I don't think you get this extended envelope phase as long lasting or as bright if you have a higher mass black hole. So I think one is I would say that the X-ray only one should be either, or it should be higher in mass. The other thing I will say is that at the very early phase, when this photosphere is very small, Steinberg and Stone show that it does make X-rays when the envelope is forming. So there could be an early phase of X-rays. So that would be my answer. Is that I think so. I was focusing more on lower mass supermassive black holes.
And since you're on this slide, I'll ask my second question if I can. So all these simulations, you throw gas on an empty-ish space, but what happens if you have a TD in a NADA of like a 10 to the minus 4 Eddington, in which I guess these sort of densities might compare to
I don't think 10 to the minus 4 Eddington will do much, but if you do have a high enough density disk, then these streams can be disrupted before they even get back to the black hole. They can be dissolved basically by Kelvin-Helmholtz instabilities and things.
Would that give you the more standard disk scenario compared to the envelope, or?
I don't know. If there's a, let's put it this way, if there's a big enough disk to really affect the streams, I don't know if this will be a huge perturbation on the accretion. I'm not sure. That's a good question. I haven't thought as much about this.
Brian, did you consider a stellar mass black hole as the incoming star? And if so, does it form a disk and maybe
Incoming star in the QP scenario, or
either one, or just the TDE?
That's a good question. So as I said, if you wanted to make, we need a big cross section for interacting with the disk. So if I just took a stellar mass black hole, moving at 0.1 c, it has a tiny cross section. I guess what's clear to me is that black hole that could then accrete, as it goes through the disk, and so that might provide a little more feedback than just its geometric, collision. You could estimate that too. It doesn't seem like it's likely to dominate, but it's a good question. I mean, it's a question of how much of this matter would actually be able to get down into the black hole that it's sort of collecting on what time scale. And but my feeling is that a solar mass black hole would not be as good as actually a physical star. But it would have, unlike a physical star, a solar mass black hole would not be destroyed.
Unlike a normal star, it would also be an X-ray emitter. If the disk
Right. So yes, whether we could detect though a accreting solar mass star in the vicinity of this would be very, very hard, I think.
Hi, I'd like to get back to QPEs. So the dynamics of the star passing through the disk seems to me it would be losing energy after each time it went through, so the orbit would be decaying. So any idea what the time scale of that would be?
Yeah, so that's a great question. So typically that time scale is a bit longer than this destruction time. So the time scale for drag to appreciably reduce the orbit of the star, we estimate, was closer to for the types of, so we're closer to 100 years. So I don't think that was partially why I didn't think it was at the very end of my talk. The fact that time scale is very long is why I didn't think it was likely, which is why I don't think in this short period of time we would expect the actual orbital period to change. Okay, because so the drag time scale just says 100 years. This is a couple years. So that's why I'm saying that whether the period is preserved or not, I think is a good test of the scenario, because I don't think the orbit should come in. Another question you might ask, a lot of people ask usually when I give this talk, is why does it have to be a TD disk? Why can't AGN disks do this too? And the answer I would have is that it's kind of a trap for the star. I think if a star had to come in through an AGN disk, it has to crash through the disk on larger scales many times. And it may not be able to survive those to get down to this scale where we could actually see the flares. So that's another thing. But the TD is great because you have nothing, and then you bring it in, and then and then you destroy it. So.
Okay, we have the room for longer if you want to stay back and ask questions, but we'll conclude the colloquium here. Let's thank Brian once more.